Right, so let's continue. As you remember, I said before we dive into instance-based learning, there are some concepts also which we still need to understand. What was that concept? Whenever you hear the keyword confidence interval, does it ring a note? Does it ring a bell to your ears? What does it actually denote? So because of that, we need to look at what? The confidence intervals for specific given constants, right? So some concepts we have to study now. So in this session, we look into what? Confidence interval for what? Discrete valued what? Hypothesis. Okay? And after this, we will look into some theoretical concepts of what? Sampling theory. So, sampling theorem or theory. Sampling theorem. So, we look at what? The basics. So, which is purely some definitions. Alright? So, I hope I'm audible enough. So let's get started. So when we say confidence interval, what does that mean? Confidence interval. So the key word here we need to understand is confidence interval. So, it doesn't mean how confident you are. Anyway. But whenever we want to dictate how good the estimate of our sample error is, we need to understand what? Whether we can actually relate this to somewhat whether we can actually relate this over some discrete value. So to understand how good our model is, right, we need to see whether this model translates into somewhat discrete valued functions. So if you remember here, we said to find the true error for what? Discrete valued hypothesis. Based on sample error, what did we do? We try to do what? Take an example. Can we actually exemplify this now? Right? So let's say we have a distribution. Say we have a distribution D, right? In which, remember, the number of instances is greater than or equal to 30. Okay? And there is a hypothesis. Instead of let's say giving D, right? And then let's say that in this, the hypothesis commits an error over what? This number of what? Examples. So we know that the hypothesis H commits, given that the distribution, okay, in which what? The number of examples is greater than or equal to 30, and that the hypothesis commits what? Error, right? So, error, let's call it R. Over what? This number of examples. Over n examples. Over n examples. Now, there are some conditions we need to understand. Given that there is no other information, only these two, given no other information, the most probable value of the error in that distribution is what? The sample error. Did you understand? This is a sample, right? And this is the distribution. And no other information was given. Thus, okay, case 1, no other information was given. No further information was given. So we can now say that such that what? The most probable value of the error. So that the most probable value of the error, that means error of what? The D, right? In this hypothesis, is what? Error of what? The sample. That's what we said. from the definition. And another thing, because we now give you another thing where you have that the confidence interval, is what? 95% probability. 95% probability. Now, the true error will lie in what? Now, this true error will lie in, I usually run out of space. Now, the true error, so I will take this up. So now we now say the true error will lies in which domain? We know it is this, right? In the sample space, right? So it becomes error of the sample given the hypothesis. Yes? Plus or minus 1.96, and I'll come to the 1.96 later. Okay? 1.96 square root of what? Square root of what? F of x into 1 minus f of x. But there is no f of x here. Square root of what? Error of the sample of this hypothesis, right? Into what? 1 minus error of what? You can't see the board. So it translates that this error lies in errors of what? Sample space given the hypothesis will be plus or minus 1.96 square root of f of x into 1 minus f of x, quickly. Square root of errors of what? Sample space given the hypothesis into 1 minus errors of sample space given the hypothesis. Now, if you get back to how we define the sample space, right? Remember we did 1 upon n? Did you remember, guys? So 1 upon n, and we are taking square root upon n. Did you understand? Without the confidence interval, the error of the sample was given like this. Summation, if you remember, we saw something. Okay, let's take only one sample now. So we saw 1 upon n into what? Errors, right? Of something, right? And that was f of x, comma h of x. Did you remember something like this? So usually we take square root to minimize this error. Hence, if you think of a value, so when we computed this error, just think that when we computed this error, we got 4. The error was 4%. Now, if you take square root of 4, we are getting 2. So this made sense, why we have to square root both, why we have to take square root. So, and confidence interval, 95% has an equivalent constant. Okay? So I will give you a table of that. So because of this, this is what the new error approximates to, based on the confidence interval. So if you get back here, you will see that we have not actually evaluated this at what? 1.3. Yes? So yeah, at what? 0.3 or 30%. For example, consider, you already know, right, that S contains what? N, which is what? 40, right? And that it commits, and the hypothesis commits what? What is that? Error, right? What is the formula, symbol for error? 12 errors, right? Now we can say, which implies that the sample error, right? The sample error is now what? R by n. Did you agree? Which is what? Because that is probability. Number of this upon total number of whatever. Fine. It's the number of errors upon total number of whatever in the sample. So we have 12 upon 40. So 12 upon 40 gives us what? Okay, let's do the maths now, since nobody is telling anything, right? So I can go by 4, right? So here I have 4 tens are, 4 threes are. Did you understand? Fine. So this is equal to what? 0.3. Or this is what? 30% error. Consider a new instance, right, that has similar attributes, in which the number of errors and the sample space was that, right? And then if we repeat this, we now know that the error will also generalize to the entire what? Distribution. Therefore, we now call this 95% in confidence interval for the what? Estimate to be the same thing for the error of the entire population, right? So we can now say that, therefore, this holds true for what? For what? Error in the entire population. Given this hypothesis. That's what we are trying to talk about here. Fine. So, we will now rewrite this for the entire population now. So we such that we rewrite as what? How do we rewrite it as? Remember, when we did this, we found this, right? 30%, right? So how do we write this as now? Error of this, see here. Error of this, right? So I'm putting it here, which is 0.30 plus or minus. Remember, we have 1.96, right? We have 1.96 into, we are evaluating this whole thing, right? So what is that error? That error into 1 minus the error, right? So the error was this. So let's do this. 3 upon 10 into 1 minus 3 upon 10 is what? 7 upon 10, right? Okay. See here. 3 upon 10 into, I'm talking about this, guys. Okay? So 1 minus 3 upon 10 is what? 0, whatever. Okay? 7 upon 10. So I'll get this. 7 upon 10. Okay, so I'm getting here 21 upon 10, 100, sorry. 21 upon 100, right? Yes, guys? So, 21 upon 100 is what I got here. So, which is what? 0.21. But remember, we are dividing it by what? N. What is N there? What is N? You've forgotten. N is 40, right? So, if I do this divided by 40 upon 1, right? So which is 21 by 100 into 1 by 40, right? So I'll get 21 by 4,000, okay? So at the end, I will get some value. Say this comes to the value of 0.07. Correct, because at the end of the day, we found something like this, 21 upon 4,000, right? Again, we take the square root. I believe this will give us 0.07. Okay, I'll find out. Okay, so if you multiply this by 0.07 and evaluate, so if you multiply this, you get what? 0.30, yes, plus or minus 0.14. So this is what it boils down to. Now, what we understood from here is, given some sets of constraints, we will actually be able to calculate both the sample error and the error for the entire distribution, right? So, with this, I will give you the constant values for respective what? Class intervals. And we will conclude the class here. And the next we look into sampling theory, some basic definition before we get into this stuff. Let's call confidence level for some number. Confidence level. So the confidence level, let's call it take for number Zn, and then what? The constant. So this is the equivalent constant. The constant value, which is for Zn as well. Now, these are proven statistically, okay? Some value, some value, some value, some value, some value, some value. Let's start. So the first value is at 50% confidence. 50% confidence. The constant we're going to use is 0.67. At 68% confidence interval, we will use what? 1.0. At 80% confidence interval, we use what? 1.28, I think so. At 80% confidence interval, we use 1.28. At 90%, we use what? 1.64. At 95%, we use 1.96. 1.96. So does it mean that we have 100%? I have not seen 100%, but what I know is we have 98%. At 98%, we use the value as 2 point. What's that? I don't know, I think 2.30 or something like that. Okay? So you can see the trend, right? That as the percentage confidence level, as the confidence level increases, the number of what? Constants also increases. Hence, you now see the reason why we chose 1.96. So if you take another example in which the confidence level is 90%, so you have to use 1.64. Okay? Sampling theorem. So we look into now definitions. Your sampling theorem. So this is purely theoretical. So if I get anything mathematical here, I will explain. Okay? Random variable. So let's take some key points now. Random variable. Random variable. Probability distribution. Probability distribution. Here mean, variance, standard deviation, and other stuff, right? And then you talk of central limit theorem. Now what we are trying to tell you here is, in random variable, a random variable is what? And just a name given to a probabilistic outcome. That's it. That is what? Dependent on the what? Experiment. So if I say I'm tossing a coin, that is the experiment, right? You must not always be in the physics laboratory or chemistry laboratory where you take some chemicals. So I'm tossing a coin is the experiment. So what are the random variables there? The head or the tail. So what are the chances that I will get head? It's equiprobable, 1 by 2. What are the chances that I will get tail? 1 by 2. In single toss of a coin. So if I toss it 2 times, now I will get total probability as 4. And each individual, I will compute that. If I toss 3 times, I will get total probability as 8. Hence, you see that was an exponential problem. An exponential problem, yes. Because the more the toss is, the more the sample space. And that leads us to what we mean by probability distribution. So probability distribution for a random variable, now we know, right? Call it random variable alpha. Specifies the probability, right, that will take the value for all possible values. So forget the theory. What is the probability that I will get a head when I toss a coin exactly once? 1 by 2. So that is what we are trying to tell here. But remember that probability can never be greater than 1. It can never be less than 0. Yes, and it can never be negative. When I say less than 0, I'm actually telling you negative, right? So the expected value now, when you hear of the word expected value, we are actually asking you of the mean value. The mean value, as you see, it is what? Is what? The aggregate of what? The values. So can we call mean as the average? Obviously. Obviously. So when you hear the word mean, or you hear what? Expected value, we are talking about what? The average. And we move to what? The variance. I think I defined it before. That the variance characterizes the what? What? The width of dispersion about its mean. Remember I said something previously that variance shows how far it is from the central mean, right? Or from the central value. So it shows, that's why we study the variance in what we call what are measures of dispersion and not measures of central tendency. Measures of central tendency here talks about your mean, mode, and median. And if you notice one thing, if you take the average age of the students in your class, you notice that the age will always be the same. There is nobody in the class that is 30 years. So maximum maybe 24 and like that, okay? 22, 23, 24, 22, 23, 24, like that, okay? So, or 21 also, maybe. So this it revolves around the center, okay? And then the one which occurs more is your model score, yes? And then you have your median, which is exactly at the center. So you see this revolves around a circle. That's why we call it measures of central tendency. But get into the standard deviation. If you are able to calculate the variance, you take the square root of variance. That gives you what? The standard deviation. Simple. Normal distribution, we should look at it. In real life, I think I gave you that instance in your class, that the age of the students is usually normally distributed about the mean score. So it shows a bell curve. Now, we will not talk about whether it is left skewed or right skewed or something. Let me take a normal distribution that is distributed around the mean. Okay? So if I see here, I might say the mean age of the students in the class is 22 years. Now, if I go to the left, I will get the same thing. Yes? Then if I go towards the right, I will get the same thing. Okay, I don't believe mostly in definitions. Can we put a finger on this definition? Yes. So we are saying something that, you know, this is called what? Normal distribution. So what we are trying to tell you here is normal distribution is a subset of your what? Central limit theorem. Is a subset of what? Central limit theorem. What does that mean? That the central limit theorem, oh, you can't see the board. So I'll repeat here again. That the central limit theorem follows a normal distribution. And as you can see from this, what I drew above, from this figure, it shows that usually some values are distributed about the center. That's what it says, about the central, or the center, about the center point. Okay? Hence, this is what the CLT is telling you. And with this, we are done with evaluation of hypothesis, motivations, estimating what? Hypothesis accuracy, sample error and true error, confidence interval for discrete valued hypothesis, and basis of sampling theory. Now we're going to dive into instance-based learning.